We're going to continue looking at finding volume like we did in our last section, but this one we're going to be learning a new method, and it's called the shell method. So we can still find the same volume of the rotated figures that we used to, but here's another method that sometimes will make things a little bit easier. With the shell method, what we want to keep in mind are the rectangles that we draw are parallel to the axis of rotation. And the way I remember this is shell and parallel rhyme. So again, with the shell method, the rectangles are parallel to the axis of rotation. Now remember, with our other method, with the disc washer method, the rectangles were perpendicular to the axis of rotation. So when we set these up, sometimes we can choose either method we want, and sometimes we'll be prescribed to do a preferred method. But what we want to remember here is whatever you do, have a good curve sketch to work with, because without the good curve sketch, whatever method we choose isn't going to really make much sense. So let's go ahead and look at the shell method, and let's see why it's a little bit different. The shell method reminds me of a roll of paper towels. If you wrap the roll, the paper towels back around the roll, it's creating a shell around the outside. So really, for the disc washer, remember, we used the idea of pi r squared, the area of a disc. For the shell method, we're going to use the idea of the circumference of a circle. So the circumference of a circle is 2 pi r. So that's how we're going to kind of start with this. And then we're also going to add a bit to it, but that's kind of the foundation for each of these methods. So for the shell method, what we're going to be looking at, again, is that idea of the circumference. We're still going to be finding volume, but we'll be rotating around an axis with our rectangles that are parallel to that axis of rotation. So I think the easiest way to get started here would be with a quick picture. So for this picture, let's say we're looking at this shape, and I want to rotate this about the x-axis. Okay, so this is my x-axis. And let's say this goes from A to B. And because I'm using the shell method, remember I'm looking at parallel, so shell and parallel, so my rectangles are going to be parallel to this axis of rotation. So because they're parallel to the axis of rotation, I'm using dy's. Okay, so for the shell method, the way this would start would be this idea of the circumference. So I'm going to have that 2 pi. Now remember, the 2 pi can go inside the integral as well. I always pull them out front because I have that coefficient out front. And my rectangles will go from A to B in this particular case. And then I need to talk about r, the radius. The radius is the distance from the middle of the rectangle to the axis of rotation. So for here, that value of r, you can see is just y. If no matter how many rectangles I draw out, I just move up y units from that axis of rotation. So that's my 2 pi r. And now I need to finish this off with the length, or the height, depending on what we're working with, length in this case of my rectangle. And the length of this rectangle would be the right minus the left endpoint. And we're going to just call this the curve f of y. And in this case, I'm touching the axis of rotation, so that would be 0. And dy is the incremental width of that. So 2 pi r times the length of the rectangle, and then the incremental width of the rectangle as well. Now that's if we are working with rotating around the x-axis. So with the shell method, remember, shell and parallel, they rhyme. Once you get your picture drawn, go ahead and sketch up that rectangle and put in your limits of integration in the picture and kind of go from there. Now we could also look at this, and we could rotate this around the y-axis. And if we rotated it around the y-axis, then I would have a different setup. So let's kind of use the same picture, but this time let's rotate it around the y-axis. And this is going to go from C to D, let's say. Now because we're using the shell method still, remember we have parallel shell and parallel rhyme. I want to be parallel to this, and so this is my rectangle, and the incremental width will be dx. So when I start to set this up, my rectangles will go from C to D. Now the distance from the axis of rotation to the center of each rectangle in this case is x. Now this one's a little bit different. Here, my upper curve, let's say, is going to be some f of x, and then this lower curve right here will be some g of x. So the height of the rectangle would be f of x minus g of x times dx, that incremental width. So this is a shell method. So I don't really memorize these formulas. What I kind of look after is shell, parallel. I know I'm using circumference because I'm looking at, taking that piece of a paper towel and wrapping it around the circumference of a circle, kind of working from there. So what we're going to focus on is the curve sketch, setting these up, and then some of them we might integrate, but for the most part I want to focus on setting these up and leave the integration to you. Okay, to get started, let's go ahead and realize that some of these can be set up using either method, but you have to be really specific in your homework. Make sure you read the directions carefully in my math lab for your homeworks and quizzes to realize what method you have to use, because it will grade you based on the method. Now in your handwritten homework or on a test, I'll tell you which method, or I will say use the method of your choice. But the important thing is to make sure you do a wonderful curve sketch, put in your rectangles, your axis of rotations, find your points of intersections, etc. So it's really important that you show all of your work. So for this first example, let's look at the graph of y equal 18x. That's a nice line that goes through the origin with a slope of 18. Y equal 18 horizontal line going through 18, and x equals 0, which is a vertical line, essentially the y-axis. And let's go ahead and rotate this around the y-axis. So we want to start with the curve sketch, and then once we have the curve sketch in, let's start with the shell method since that's our new method here. But let's worry about the curve sketch first. Okay, so y equal 18x. That's a very steep line that's going through the origin with a slope of 18. Y equal 18 is a horizontal line going through 18 on the y-axis, and then x equals 0 is our y-axis. It's this vertical line right here. So this triangle is basically the shape that I have here, and this is the shape that I'm going to rotate. Now we're going to rotate this about the y-axis. So we'll put in our rotate symbol, and then we'll kind of look at this, and sometimes one method is easier than the other depending on how my equations are set up, but sometimes I can just rewrite my equations too and make them work. So again, it depends on which rectangle you're drawing, a horizontal or a vertical. Okay, so when we put in our axis of rotation here, we're rotating this about the y-axis. So here's my y-axis, that's the same as x equals 0. So setting this up, let's go ahead and start with the shell method. Now remember, with the shell method, we're parallel to the axis of rotation. Okay, and also remember this starts out 2 pi r. Think about circumference. So if we're parallel to the axis of rotation, let's go ahead and put in our rectangle here. So putting in our rectangle, we can see that our incremental width would be dx. I'm parallel to the axis of rotation, so this would be volume equals 2 pi integral. It looks like to me I'm going to go from 0, and then I need to figure out what this point is. Okay, so how would we figure out that point? Well, it looks like to me this is y equal 18, and so if I want to figure out what's going on for my x value, I could only get y equal 18 if I plugged in x is equal to 1. So x equal 1, 18 times 1 is 18. So this is going to be the integral from 0 to 1. Now the distance from the axis of rotation to the center of any of the rectangles that I draw is going to be x. So no matter where I draw my rectangle here, the distance between the axis of rotation and the center of the rectangle is x. Okay, now I need basically the height of the rectangle. Well, we can see that the height of this rectangle is going to be 18, but I have to subtract off the bottom part, and that bottom part is 18x. Okay, so here's my setup. 2 pi r. R is the distance from the axis of rotation to the center of the rectangle. The height of the rectangle is 18, and then I'd subtract off the bottom of the rectangle, this piece right here, 18x dx. Now I'm going to let you go ahead and integrate these so you can practice your integration. I want to worry about the setup. To integrate this one, you'd want to take the x and distribute it through and then just use your good old power rule. But when I integrate this, I do get 6 pi. Okay, let's go ahead, and even though it might not be asked for, I would like to look at this using the other method as well, the disc washer method. Now whether it's a disc or a washer will depend on whether there is a hole in the rectangle or not, whether I'm touching my axis of rotation. I don't know why that keeps disappearing. Okay, so let's go ahead. This was my rectangle for the shell method. Now if I use the disc method, and it's a disc method because I'm touching my axis of rotation, you can see that I need to be working with dy's. So this is where I'm perpendicular to the axis of rotation. Now remember, with the disc method I'm working with area. So we kind of need to think pi r squared here. That's kind of how we'll develop this. So this is a dy here. Now this curve y equal 18x, because this is a dy, I need everything in terms of y. So I need to solve for x, and if I solve for x, I get x equal y over 18. So this is the curve that I need to be working with right here. So to set this up, volume is pi. These will go from 0, these horizontal rectangles here, to 18. And then I need my outer curve, which was y over 18 quantity squared, my outer radius minus my inner radius. And because I'm touching the axis of rotation, that inner radius is 0, and this is incremental width is dy. So you need to be able to flip back and forth between these two methods. Either method you use here, I'm going to get 6 pi because the area that I'm rotating is the same, and so is the axis of rotation. So I get 6 pi here for both of these volumes. So this would be 6 pi units cubed. So again, it's important that when you do these on your test and on your handwritten homeworks, that you have a nice curve sketch, that you show your rectangle, you name your method, you write out whether you're parallel or perpendicular, you have the axis of rotation, and you also have the limits of integration on your graph and of course with your integrals. And when you integrate, you'll show all of your work to receive credit and leave your answers in exact form, so you don't have to really be worrying about decimal approximations or using a calculator. So be very, very thorough when you're setting these up. It'll help you get to the correct solution. Now sometimes with the problems that we set up, getting to the graph is the tough part. On our next one, we're going to be looking at one that's specifically asking for the shell method. So again, be careful with the homework you're on because it might ask you for a specific method. Most of these I'm going to set up both methods just so you can see them as an example. So for this one, we're taking the graph of y equals square root of x, y equals 0, x equal 144, and I want to rotate this. Let's do this one, rotate this one about the x-axis. Okay, now in your homework, be very specific about what method you're looking for. Make sure you read the directions. I'm going to be setting up both methods whenever possible just so you can see the differences. So if we set this up, knowing our basic graphs will be important. On your handwritten homeworks, Desmos, D-E-S-M-O-S, is a very nice online graphing calculator to use if you would like to check your graphs and to help you get started. So y equals square root of x is a graph that looks like this. Y equals 0 is going to be this horizontal line. Here's y equals 0. And then we also have x equal 144, and I'm just going to make this up. Here's x equal 144. Now I'm rotating this about the x-axis, so here's my axis of rotation. So I want to take this region, and with this region rotating it about the x-axis, usually one method is easier than the other. Now if you look at our original equation that was given to us, it's y equals square root of x. So what that is, that's already in terms of x. So if I could have my rectangles in terms of x, meaning touching the x-axis, that would probably be the easiest setup for me. So let's go ahead and think about our rectangles touching the x-axis, because this is already in terms of x. Well, if we look at it this way, you can see that I'm perpendicular to my axis of rotation. So to start with, on this one, I would want to look at the disc washer method. Now in this particular case, if I'm taking this and I'm spinning it around this axis, I'm touching my axis of rotation, this would be my disc method. Not a washer, but my disc method. Now remember, for the disc method, I am looking at is perpendicular to the axis of rotation. So the rectangles are perpendicular to the axis of rotation. Okay, so let's go ahead and set this up. Now I know this section is on the shell method, but I just want you to see that a lot of times you can use either method. So with the disc method, we're perpendicular to the axis of rotation, and kind of our template for remembering what to do here is pi r squared. So I have the pi out front, and then I have my limits of integration, and the limits of integration along the x-axis will go from 0 to 144. And then I have my outer radius, which would be the square root of x squared, because it's r squared, minus my inner radius, and I'm touching the axis of rotation, so that's going to be 0. And the incremental width of that rectangle is going to be dx. So this sets up pretty slick, and if you want to go through and integrate this and check it, you absolutely can. And you get some pretty big numbers here. You get 10,368 pi. And this is volume, so this would be units cubed. Now, on a test, absolutely I would expect that you could sketch this picture, set up both disc and washer method. Getting these big numbers I'm not so worried about. You'd probably have a more reasonable number up here for your upper limit of integration, let's say something like 10, that you could actually work with. But you would be expected to work a problem similar to this. Now let's go ahead and look at the shell method as well. For the shell method, remember that my rectangles are parallel to the axis of rotation. And we're looking at circumference here, so we want to think 2 pi r. So my shell method, if I'm going to be parallel to the axis of rotation, what I'm doing then is I'm taking my rectangles here and I'm rotating them, these green rectangles, because I'm parallel to the axis of rotation, which is basically this y equals 0 or our x-axis. So to get started here, this is going to go 2 pi. Our limits of integration definitely start down here at 0, and they go up to whatever this point is, and so we haven't identified that point yet. If I plug 144 in to my y equal root x, the square root of 144 is 12. So my limits of integration go from 0 to 12. Now the distance from the axis of rotation to the center of any of these rectangles is going to be y. And then I need to talk about the length of the rectangle. Now to find the length of the rectangle, you basically take the right endpoint minus the left. So the right endpoint is going to be 144 minus the left endpoint, which is this curve, Well, the curve is y equal the square root of x, but remember, everything here has to be in terms of y. So I need to solve this for x equals stuff in terms of y. So I'd square both sides, and I'd have x equal y squared then. So this would be 144 minus y squared. Now this to me looks, the shell method on this one looks to me a lot harder than the disk method in terms of the integration. But either way you integrate this, you get 10,368 pi, and again units cubed. So when you're setting these up, a curve sketch is essential. Sometimes one method is easier than the other. Make sure you look at your instructions, because with your instructions we'll kind of go at some other information about which method is expected. Sometimes you'll be asked to use a particular method, and sometimes you'll be allowed to choose which method you would prefer. The next one we're going to be looking at, as usual, will have a very important curve sketch, but the axis of rotation is what's interesting about this one. So let's go ahead and look at a familiar graph. Let's look at y equal x squared. This is a parabola with a vertex at the origin opening up. Y equal 4. And then also let's look at x equals 0, which is the y-axis. And let's revolve this around the line y equal negative 6. Now the reason this one is different is most of these that I've set up have been always rotated about an axis, not a line, y equal negative 6. So let's go ahead and get started with our curve sketch. Now for this one, I'm going to have to be able to drop down into y equal negative 6. So I need to leave plenty of space down here. And I have a parabola opening up. We'll make this up to say this is y equal 4. Here's x equals 0. That's this region right here. So I'm taking this region right here, and I'm going to rotate this about the line y equal negative 6. Now usually I'm using an axis, either the x or the y-axis, but in this particular case I'm using an entirely different line. Now we have to be really careful about this type of problem, because I'm going to have an upper and a lower, a right and a left endpoint that we have to be really careful about keeping track of. And what's even trickier about this one is that we skip across from the positive region into the negative region. Okay, so the things that we keep track of here will be really important. So when we put in our axis of rotation, that's going to be clear down here at y equal negative 6. So this is my axis of rotation. Okay, so when I'm looking at this right now, let's go ahead and try, let's do the shell method, I guess. So we'll do the shell method to start with. Now remember, always write out after you have your picture what method you're using and tell what your rectangles are doing. So with the shell method, the rectangles are parallel, shell parallel, they rhyme, to the axis of rotation. So we're parallel to the axis of rotation, and remember for the shell method we want to think about this as circumference, so let's think about this as 2 pi r to get us started. So volume here would be 2 pi. Let's go ahead and sketch in our rectangles. We're parallel to the axis of rotation, so this is what my rectangles would look like. The width here is a dy. My limits of integration will go from 0 to 4. The distance from the axis of rotation to the center of this rectangle isn't y. If you count up here, it's going to be 6 units and then plus y, depending on where my values move. But another way that we could think about this is we could think about this as the upper minus the lower. So this would be y minus a negative 6. So again, your upper minus your lower curve will give you that distance of y plus 6. Then what we can also have here is the length of this rectangle. Well, the length of this rectangle is going to be this curve. Now y equal x squared is the curve, but this has to be in terms of y. So if I take the square root of both sides, I get square root of y equals x, and this would be a plus or minus square root of y. So x equal plus or minus square root of y. Now I'm going to use the plus square root of y, because if you notice, all my x values are positive in the first quadrant, so I'd use the x equal the positive values. So this would be root y and then minus 0 dy. Now it's minus 0 because it's touching this axis. So my right minus my left touches that axis. Now you'd want to simplify this a bit. Obviously root y minus 0 is just good old root y, and minus a negative is the same as a positive here. So I could simplify this a bit to y plus 6 times the square root of y dy. And if you want to integrate this out to double check your work, and this would be a totally reasonable one to do, it would be 448 pi over 5. Okay, so that's the shell method, and I think the shell method is pretty straightforward on this one. Let's go ahead and look at the disk slash washer method. Now remember, with the disk slash washer, it's the same method, it just depends on whether we're touching the axis of rotation. And for this one, you can clearly see we're not touching the axis of rotation, so it would be washer. So rectangles are perpendicular to the axis of rotation for the disk washer method. And for this one, I want to think area, so I'm going to be thinking pi r squared. So pi, and then I need to look at my limits of integration, and then I have my outer radius squared minus my inner radius squared, and this would be dx's. Now I know it's going to be a dx because when I draw my perpendicular rectangle, it cuts the x-axis, and the incremental width of this rectangle is a dx. Okay, so limits of integration. They will go from 0, if you look at the green rectangles, they'll go from 0, and then my other one, it's going to be whatever this point is right here. So if I wanted to figure out what that was, remember this is y equal x squared. So if 4 equals x squared, x would equal 2 on this side, negative 2 over here, but we're just looking at this first quadrant information. So my limits of integration go from 0 to 2. And then I need this length. I need the upper, and that's going to be 4 upper minus lower, 4 minus a negative 6. And then, so that 4 minus a negative 6 we can see is 10 units. And then we need to kind of chop off this piece that we don't want. So to cut off this piece, I'll be subtracting off this lower curve. Everything is in terms of x, so I can just plug in that x squared. So this is going to be set up as your upper minus that lower piece. So this upper was the 4 minus a negative 6, and this lower piece would be the x squared minus the lower piece, a negative 6. So that would again be that upper minus the lower. Now we can simplify this quite a bit. So I'm going to integrate from 0 to 2. 4 minus a negative 6 would be the same as 4 plus 6 is 10 squared minus x squared plus 6 quantity squared dx. Now if you integrate this, remember that you have to FOIL this out first, outside insides lasts. You don't want to just take the 2 and distribute it. That's not a mathematically sound thing to do. Either way, either method you choose, you'll get 448 pi over 5 units cubed. And again, I'll leave the integration to you to practice with. I want to focus on setting these up because some of them can get pretty complicated. And if you get stuck on your integration, take a screenshot of what you have and I'd be happy to help you out. Okay, for our next one, I want to set up both methods. And sometimes you'll be asked to set up both methods in your homework or on exams or your handwritten homework. So this one I'm looking at y equal x to the 1/13th. And I want to look in quadrant 1. And I want to rotate this about the x-axis. Okay, so we need a picture. I think the easier part of this picture will be y equal x. We know y equal x is this line that bisects the first and third quadrant at a 45-degree angle. Let's make it look like it actually bisects something. So this is y equal x. And then this piece right here, this next piece, y equal x to the 1/13th, this is kind of an interesting one. Y equal x cubed would be kind of this S shape. y equal x to the 1/13 is going to be similar but just scaled differently. So it kind of looks almost like this. And again, if you're not sure about these, the best thing to do would be to graph these. You could graph them on your graphing calculator. I like to use Desmos on my computer. They give such a nice curve sketch. It's really nice to be able to work with a nice curve sketch like that. On a test, you would probably need to plot some points if you weren't sure what this looked like. So this is my graph. I need to find my points of intersection. My other ones have been pretty straightforward so far. So for my points of intersection, I can set these equal to each other. Now there's quite a few different ways that you could look at these points of intersection. When I'm trying to solve here, the first thing that I could do when I'm setting this up is to look at the exponents, and I think the easier thing to do here is to probably take the 13th power of each side. So I'm going to do that instead. So at this point I'm going to raise both sides to the 13th, and I'll get x to the 13th equals x, and then I'll subtract that across. Factor out the x to the 12th minus 1, x equals 0, x to the 12th equals 1, so this would be x equal 1. And we could also have a negative one here, and that would be this point. But we're only in the first quadrant, so I'm only going to worry about x equals 0 and x equal 1. So here's x equals 0, here's x equal 1. When I plug a 1 in, I get a 1 back out. So there's my points of intersection, and now we'll go ahead and set up both the disk and the washer method and the shell method. Now my axis of rotation is the x-axis, and as I'm looking at this, I think this will be our easiest case right here, is if I'm perpendicular to that axis of rotation, because everything is in terms of x and that rectangle is in terms of x as well. So this would be a disk washer. Now because I'm not touching the axis of rotation, technically it's a washer method. This is when our rectangles are perpendicular to the axis of rotation. And remember, for this one we think area, pi r squared. So to get started, we have volume equal pi. My limits of integration will go from 0 to 1 along the x-axis for that rectangle. And then from here I need to think about my upper curve, and my upper curve in this case is x to the 1/13. So my upper curve, my outer radius squared minus my inner radius squared, and my inner radius is this x line dx. So this is the appropriate integral that I set up, and again this is a totally reasonable integral to work by hand. I'd get 8 pi over 15. So make sure you're working through these integrals, because it's important that you know how to integrate these. The reason I'm not spending time on them during the lectures, these lectures would probably be 2 hours long at least if I worked through each of these integral problems. But all of these use integration techniques that we're familiar with. Let's go ahead and look at the shell method. Now remember, with the shell method, the rectangles are parallel to the axis of rotation. Shell and parallel, they rhyme. And here we want to think circumference. So this would be 2 pi r. So my volume here would start with 2 pi. Now let's go ahead and have a look up here. If I sketch one of these in, this is parallel to the axis of rotation. You can see that my incremental width here would be dy. So everything here has to be in terms of y. My limits of integration go from 0 to 1 again, but on the vertical this time. The distance from the axis of rotation to the center of this rectangle is just y units along the y-axis. And then the length of this would be the right minus the left endpoint. So the right graph is y equal x, and everything's in terms of y, so that's just going to be y. And my left endpoint is this graph of y equal x to the 1/13th. But I need to solve this in terms of x, so I'm going to raise both sides to the 13th power. So this would be y to the 13th dy. Now I did the same thing here with y equal x. I just flipped that around and said x equal y. So this is my outer radius, this is my inner radius, right minus left. Now no matter how you choose to set this up, you're still going to get the same solution of 8 pi over 15. So again, make sure you take the time to run through the integration to match these solutions. In order to integrate this particular problem, you'd want to distribute the y first before you integrate it. Now I believe when you put these in my math lab, I don't know if you can put the 2 pi out front. So if it doesn't let you put the 2 pi out front or doesn't like that as a solution, make sure you put it on the inside of the integral as part of the integrand. So again, a good curve sketch is the best way to start most of these problems. Okay, one type of problem that we might not be familiar with is something like a 5th degree polynomial. So some of these can get to be pretty difficult in terms of graphing. So I encourage you, like I said, to graph these. You could graph them on your calculator if you'd like, but the basic graphs you should know or be able to plot points to figure out for your handwritten homework. Of course, double check them online and with a calculator, but on a test you'll need to make sure that you know those basic graphs. So to get started with this one, let's go ahead and look at, let's see, what kind of a graph haven't we looked at yet? Let's look at one that's bound above and below by different curves. So let's look at the solid formed by y equal x squared, parabola opening up with a vertex at the origin, y equal 8 minus x squared, parabola opening down with its vertex 8 units up from the origin. And let's rotate about the, let's do the x-axis. And this one, we could do the method of your choice, or let's set them up both just so they're familiar. So we talked about y equal x squared. That's a parabola opening up with its vertex at the origin. And then our other one, y equal 8 minus x squared, is a parabola opening down 8 units up on the axis, on the vertical axis. So this is y equal 8 minus x squared. So this is the region that I'm trying to rotate. And if I look at the region that I'm trying to rotate, let me see if I can get this to highlight. You can see that there's definitely going to be an advantage of one method over the other here. Mainly because if I use horizontal rectangles, I have two regions. I have a region above that uses the purple graph for my right and my left endpoints, and then I have a region below that uses my right and my left endpoints for that graph as well. So we have to be pretty careful about how we decide to set this one up. There's an easier way and a harder way. I think one thing I forgot here was my axis of rotation. I need to make sure I have that written in. Okay, so if you notice, if I put in a horizontal, I'm going to have two regions. I'll have a region above and a region below that have different right and left endpoints. So it's to my advantage to use vertical rectangles. So I'm going to start out with vertical rectangles. Now if I use vertical rectangles, the incremental width is dx, and you can see that I'm perpendicular to the axis of rotation. So this looks like to me that it's a disk washer problem. Now because the entire graph is not touching the axis of rotation, it would be more of a washer issue. So I have rectangles that are perpendicular to the axis of rotation. So if my rectangles are perpendicular to the axis of rotation, I'm thinking about that pi r squared. I'm looking about area here. So to get started, I'd have my pi. Now these are going to go from whatever this point is to whatever this point is over here. So in order to find my points of intersection, I need to set these equal to each other. Now when I set these equal to each other, I have x squared equals 8 minus x squared. I'm going to come up with x values, so I'm going to come up with these numbers down here. And I also want to find the y values as well. Moving the x squared across, I have 2x squared equals 8. Divide through by 2, x squared equals 4. Take the square root of both sides, and I have x equal plus or minus 2. So this is negative 2 and positive 2. And then, if I plug that in, this height is 4. 2 squared is 4. Negative 2 quantity squared is 4 as well. So these vertical rectangles will go from negative 2 to positive 2. Now my outer radius, or my upper radius, is this purple curve, which is 8 minus x squared. And that's going to be quantity squared. Minus this lower curve that we'll cut out would be x squared, quantity squared dx. So that would be the setup for my disk washer for this particular problem. And if you go through and integrate this, you get 512 pi over 3. And again, make sure you practice integrating these, because that's a big portion. After you get these set up, you should be able to integrate them. Let's also use the shell method. Now the shell method is going to be more difficult for this one because I have two regions. Now let's remember, shell method rectangles are parallel to the axis of rotation. And I want to think about circumference here. So that would be 2 pi r. So setting this up, I have 2 pi. Now I have two regions, so I better make sure I leave room for that. My first region is going to be below, so I'm going to call this region 1. And my second region will be above, and this will be region 2. Now the reason I say above and below, because below, if you notice, I have a different right and left curve, so I need to switch when I move to a different right and left curve on the top part. So you have to be really careful about how you set these up. So to set up the shell, I have region 1 plus region 2. So let's go ahead and look at region 1. Region 1 would be 2 pi. These rectangles will go from 0 to 4. The distance from the axis of rotation to the center of any of these rectangles will be y. And then the right curve, this is kind of what we want to focus in on. My right curve, it needs to be in terms of y because my incremental width for each of these horizontal rectangles is y, dy. So if I take the square root of both sides, I get x equal plus or minus root y. So this on this side would be the plus root y, and over on this side would be a negative root y. So my right minus my left would be root y minus a negative root y. Okay, so that is my right minus my left dy. So this is region 1. And then plus my region 2, that my rectangles will go from 4 to 8. The distance from the center of the rectangle to the axis of rotation is y. And then over here, I have y equal 8 minus x squared. Solving, I have x squared equals 8 minus y, square root of both sides plus or minus root 8 minus y. And again, this would be root 8 minus y over here. This would be negative root 8 minus y over here. So I have root 8 minus y minus negative root 8 minus y. And of course, my bracket is here, dy. Okay, so I kind of had to squish it in there. Now, if you work through this, just as we worked through the other problem, there's a lot of simplification that can be done here. And again, this is my first region, 0 to 4. This would be y. Root y plus root y is 2 root y, so this would be 2y root y dy. That's one way that we could write this. Now if you want to pull the 2 pi in, this would be 4 pi y root y. And my next one would be 2 pi integral from 4 to 8. So this would be y. This would be another 2, so this would be 2y root 8 minus y dy. So some of these will be a little tricky for integration, but I think this one particularly, I like this one, will be fun. So double check these 512 pi over 3 because you want to make sure your integration skills are sharp. Now when you're setting these up, definitely to me, for this particular case, the disk washer was easier because I just had one method. So if you have the option of choosing whether you're using horizontal or vertical rectangles, you should look at it and decide, you know what? It looks like to me if I choose the vertical rectangles, I only have one integral that I'm going to be working with, whereas another method I might have more than one integral. So it's worth your time to do a nice curve sketch and then to analyze what you have to see if one method will work better than the other in terms of a simpler integral. Now the last problem that we're going to be working with, they don't give us an equation. What they give us is the name of a shape. So let's go ahead and start looking at this problem. We could use, well, we'll talk about the method that we're going to use here in a bit, but what we want to start with here is a right circular cone. So we have a right circular cone with a radius. So the radius is equal to 8, let's say, and the height is equal to 12. And then what we do is we drill a hole right down the middle of this solid that's formed with this right circular cone that's rotated about the x-axis. And the hole that's drilled has a radius of 3 centimeters. I guess the fact that it's centimeters doesn't matter here. Okay, so let's go ahead and get started with what this looks like. We're going to draw a couple different pictures here. So first of all, right circular cone, just so you kind of have an idea of what it looks like. This would have a radius of 8 and a height of 12. So let's say our height is 12, and here's our radius of 8 units out. And what we would do is we would take this and we would rotate it. So what it ends up looking like is something like this. So height is 12, radius is 8. So we're going to take this shape, you can see, and to get this shape over here, we would rotate this about the y-axis. So if we rotate this about the y-axis, that will kind of give me an idea of what this shape will look like. Now we haven't even talked about the hole that's being drilled. But right now, before I even start, I need to find the equation of this line, and then we'll worry about the hole that's drilled. So, the equation of the line. Well, right now, pretty clearly I can see that my y-intercept is 12. And then I can also find my slope because I have 2 points here. So one point is 0, 12, and the other point is 8, 0. So my slope would be that change in y over the change in x. So I'd have 12 minus 0 over 0 minus 8. So 12 over negative 8 is a negative 3 halves. So the equation of my line then is y equal negative 3 halves x plus 12. So that's the equation of this line, y equals negative 3 halves x plus 12. Now let's worry about that hole. Now the hole that we're going to drill is down the axis right here. And it says to go out 3 units. So let's go out here to 3 units and drill that hole. So this entire area will be empty, and then when I rotate it, basically it'll have a hole right down the middle like this. So the distance here that I'm left with from 3 to 8 is 5 units. So let's go ahead and set this up. I think in looking at this that the shell method is probably going to be easier here because I have that incremental dx and my equation is already in terms of x. So let's go ahead and use the shell method. Okay, now remember with our good curve sketch we always have to write which method we're choosing to use. So for the shell method, my rectangles are parallel to the axis of rotation. And I need to think here about 2 pi r. So setting this up, I get volume equals 2 pi. Now, if I'm parallel to the axis of rotation, our rectangles will go from 3 to 8. The distance from the axis of rotation to the center of this rectangle is x units. Now the upper curve is -3/2 x plus 12, and then the lower curve touches the axis, so that would just be subtracting 0. And of course the incremental width is dx. Now of course you can simplify this. The -0 kind of falls off there. When you integrate this, you'd get 175 pi units cubed. So you distribute the x and then use the power rule and integrate and evaluate. So some of the things I want you to remember here is on your handwritten homework, on an exam, the setup is very important, but so is your integration and showing all of your steps of integration. You do not want to skip any steps because that's where credit is given. On your My Math Lab homeworks and quizzes, obviously they're not checking, but I would practice it so you get in the habit of showing all of those steps. As usual, if you have any questions, let me know. I would use your graphing calculator or Desmos or Mathway to check your work for your My Math Lab and check your work for your handwritten homework. But you have to make sure that you show all of your work for your handwritten homework and your exams. If you have questions, make sure you send me a screenshot, or you can let me know and we can meet online for some office hours. And you also have the help from Pearson Connect. Good luck and enjoy this assignment. It's kind of fun.